Hi, welcome again. It's important that we can locate accurately how objects move in real life in order to represent these inside VR, since virtual reality is about emulating and altering reality. So, for a good experience, a turn of the head should result in a corresponding change in the visual display, and the perceived sound direction is invariant to the orientation of the head. The speed and fluidity, the smooth movements with which the image on the display changes in response to the observer's head movements, they become nowadays more and more closer to the visual feedback observers observe of experience in real world. Matching these movements requires body tracking, at least head tracking, but generally the greater degree of body mapping, the greater the extent to which the movements of the body can accurately reproduced. So the subject of this week is about tracking, and this is another piece of the puzzle of immersive virtual reality. It's about how position and orientation of a user or a body part of a user can be acquired from the real world and used in the virtual world. VR systems need hardware devices that monitor the user. This has to be done real time so that the user action in the VR experience and the rendering of the VR world is from user-centric perspective. Without this ability, a computer-generated display is not interactive. It's clear that devices that provide a natural navigation and interaction in the VR world also provide a higher feeling of immersion. And with this in mind, researchers developed all kinds of systems with all their own advantages and disadvantages. But to make a good choice of these different technologies, the use in which situation, you need to know something of how they work and what advantages and disadvantages they have. So what is tracking? A tracker is a special purpose hardware used in VR to measure the real-time changes in object position or an orientation. VR systems track at least some part of the body. For example, in our case we use head tracking, and sometimes we use hand tracking with the use of gloves. And we also have a complete body motion tracking system. You will do this tracking in a practical assignment with OptiTrack. So that's how the name is of the system. Often position sensors are used to track the participant's head, limbs and participant's hands. For head tracking, often only orientation tracking is used. A tracker system has often a sender and a receiver, but more and more we see IMUs, that this is an inertial measurement unit. For example, see this picture. They are cheap or small and used in a smartphone and in Wii modes. Use of tracking. When you can track, what can you do with it? You can use view control, this means position and orientation controls with virtual camera rendering, so you have a first person viewpoint. Navigation orientation, to point in a certain direction and to fly in that particular direction. And also sensors could detect walking in place. You make a motion for, you get a kind of further strolling. And then object selection and manipulation. Tracked handheld devices let users grab physical surrogates for visual objects and manipulate them intuitively. Track gloves acting as virtual surrogates for users' hands and let the user manipulate virtual objects directly, and often the user can ask the selected object for information. Instrument tracking, think about track tools and instruments that you match virtual objects with their physical counterparts, for example computer-aided surgery or mechanical assembly. And at least after examination, perhaps the most conspicuous and familiar use of trackers, it gives a realistic moving, animating characters by with full body motion capture with the mocap, and this can be done on human actors, animals, and even on cars. But before you buy a tracker, an important question is to be answered first. What kind of actions are expected? Walking, grabbing, swimming, running, bicycling. So that's an important question to be answered first. So orientation and position. The different trackers have 6 degrees of freedom. The degree of freedom are the set of independent placements and rotations, and that together specify completely the position and orientation of a body or system in 3 dimensions. So independent means a change of one doesn't change the other one, okay? To figure out the rotation of an object is easily done with a gyroscope. So like in a plane, it gives 3 rotations, Z pitching and X rolling and Y yawing. The first Oculus Rift provided only 3 degrees of freedom, rotational head tracking, which is not positional. While you will be able to look around at the virtual reality world with the first Oculus by tilting and turning your head, you weren't able to lean down to inspect objects on the floor or lean around corners, because there's no way to tell exactly where your head is. So orientation tracking can be done with an old simple instrument, the gyroscope, and in the face-to-face lessons we talk more about this device. And the position tracker is the most important tracking device of any VR system. Position tracking tells the VR system what the users are located within the VR space. So realize that the first Oculus hadn't position tracking. The ability to accurately detect translation movement is highly desirable for reality. Think about the last slide, changing the viewpoint of the user to reflect actions such as jumping, ducking, or leaning forward. And connecting the physical and the virtual world needs position tracking too. For instance, by detecting a hand position, you can program the option to move virtual objects by touching them. But that's only possible if you know the position. So how can you choose the best method? The VR world needs to know where the user is. Although it's not our objective to look at today's technology in detail, we will use some examples of existing technology to illustrate. The projects are changing rapidly, but the concepts behind remain the same. Note that trackers impose limitation on the system. Of course, limitations vary with the type of sensor employed, but in general, limitation arise from the technology used to determine the relationships on some fixed origin and the sensor. For example, some trackers require an uninterrupted line of sight between a transmitter and a sensor. When the line of sight is interrupted, the tracker system cannot function properly. With present state of hardware development, there's still no all-embracing method of sensing everything we would like to be able to sense within a real-world space. Some currently developed systems work better on small scale and some work better on large scale. Some work more accurately than others, and some sense things that others can miss. But no available technology at any cost provides optimal conditions in all areas. The system designer must how the VR system will be used and make optimal trade-offs. So there's no complete right answer for the best tracking method. There are many factors to weigh. For example, what kind of tracking accuracy is required, what is the refresh rate that is required, whether objects to be tracked are well known or can change from time to time, whether objects tracked are rigid or flexible? What's the room of tracking, the tracking area? Yeah, also is the tracking to be done indoor or outdoor, and what are the lighting conditions? Is there enough power available? And of course, what are the costs? So here on the slide, on the slide you see some criteria summed up. First, accuracy, the measure of the error in position and orientation of the track's value, and that's passed. So that depends also on the operating range. Resolution, that's a smaller change in position and orientation that can be tracked by the tracker. So that's different from accuracy. Range of working room, that's the amount of space where a tracker works. So the volume wherein the tracker can measure the position and orientation with a certain accuracy and resolution. And then frequency and speed. That are the number of times per unit time that position and orientation measurement are transmitted to the computer system. So also called update rate. Are the measurements a second. Then latency, that's the delay between the change of position and orientation and the real change of the system. So also called lag. Noise and instability, that's inaccuracy and noise, where the tracker reacts on, so drift and signal ratio and that kind of things. In the time, drifting, time drifting. Multiple objects independently determine the position of multiple objects. Is that possible, or just one object? How many objects? And the last is the form factor. That's the size and the weight of the tracker sensor. So especially registration in augmented reality requires extremely fast and accurate tracking. Ideal is high accuracy, high resolution, high frequency and low latency. And the system should be scalable and of course easy to use. That would be the best system. So a tracker on a chip, that's an ideal tracker. It is from the article on the intranet called Tracking Silver Bullet. But it has contradictory features. See the opposing interest, like costs against accuracy. So it's impossible to make something like this. From sampling the position and to rendering with this information next frame takes time. It can't be done instantaneously. There are several steps in series with potential important delays between each, as you can see here in the picture, and they are summed up here on the slide. Of course you want to minimize it because it has several negative effects on the simulation. It spoils the experience, you can get similar to sickness of it, objects appear where they are not, and that gives conflicts. You are as a user forced to adapt on that situation. So the tracking systems introduces a delay between the real world event and the corresponding movement in the VR scene. If you want to know the overall latency, you can't simply deduce this from the values from the manufacturer's specifications. So how can you find the lag? An easy example is written in an article by Stuart Gilson and Andrew Glenister. They describe how to do it. They record with a video camera a tracked object that's being moved in a roughly sinusoidal motion, and also a computer monitor is filmed with the VR scene and the tracked object. And with some image processing, the difference can be calculated between the two pictures, and with the known refresh rates of the monitor and the camera and the amount of time the PC spends on decoding coordinates and rendering, you have a part of the total latency. So the value can be subtracted from the calculated value, and you obtain the delay introduced by the tracker and some of the communication protocol. And in this way you can discover the source of a delay. So latency you can see as a temporal accuracy. In this picture you see a spatial accuracy and resolution. It is the difference between the actual position and the reported by the tracker measurements. So it is not the same thing as resolution, because resolution is the minimum change that a sensor can detect. So this value of accuracy depends also on the operating range. Typical accuracy is degraded with distance from the origin of the reference systems of the coordinates. Jitter. If the tracked object is stationary, then there still can be a change in this tracker output, and that's called jitter. A tracker with no jitter gives constant values as output if the object is stationary. Also jitter should be minimized because it gives unwanted effects in graphics like tremors, jumpy virtual objects. Jitter can be filtered out but this operation can give some more latency. Drift is happens as time passes. This is as the tracker accuracy grows in time. So there's a steady increase in tracker error with time. And the last one is sociability, and that's all about how many users you can be, what is the operation range, is interaction possible, is it wearable, that kind of questions.
So let's talk about some types of trackers. Here you see a classification by operational principle. So magnetic, that's with alternate currents, direct currents. Optical, can be with markers or without markers. Acoustic, a way of tracking, that's with measuring the time of flight of sound waves. Mechanical, that's with a skeleton fixed on the user. Inertial, that's are the IMUs I talked about earlier. You use a gyroscope, acceleration, and some hybrid forms that are combinations of multiple tracking concepts. So let's first start with inertial tracking. So it's a combination of sensors, accelerometers, gyroscopes, and magnetometers. Here you see all kinds of properties of these devices. So accelerometers, that are devices that measure acceleration along the axis. A triaxial accelerometer can be used to obtain not just the netto acceleration but also its direction. In practice it actually measures force with a device such as the piezoelectric crystal. Such crystals generate a voltage that responds to light mechanical stress. So a relation between force and voltage is known. And then the acceleration is determined by using Newton's second law. So it can be used to determine the object's position if the starting point is known. But the requirement to integrate the signal because of Newton's second law to obtain the position and orientation, the measurement is the main source of error in inertial tracking, because the error sums up to a bigger error and tends to cause drift unless the sensors are calibrated regularly. Otherwise, yes, they accumulate. So this device works very well over short periods of time and can work at high frequencies too. So the gyroscope is a sensor that measures the components of an angular velocity about its axis. It can be used to continuously read the difference between the current orientation and the previous one. So, in practice, they aren't really gyros. They are too big for tracking. But the same principle can be used with tuning forks. They are small. So a magnetometer is often used for better calculation of the direction because it uses the Earth's magnetic field direction as an extra information source. So you can use that to calculate better values. So inertial trackers are often used together with other types of trackers. So magnetic tracking. Magnetic tracking gives the absolute position of one or more sensors. It can be used to measure distance and orientation. They consist of a transmitter and a receiver. They both consist of 3 coils, antennas, and they are arranged orthogonally, so perpendicular on each other, as you can see on the slides. So we have 3 dimensions. The transmitter emits each of these its 3 coils in sequence and introduces in that way currents in each of the receiving coils. Because magnetic induction in the sensing coils depends on the distance from the field generating coils and also the angle that makes with the field, the position of the receiver can be calculated relative to the transmitter. So the strength of the measured signal is compared to the known strength of the emitted signal. We had to calculate the distance. So by comparing the 3 induced signal strengths among cells, the orientation also can be determined. There are 2 types of magnetic tracking technologies: low frequency alternate current fields. So the frequencies are between 7 and 14 kilohertz, or pulsed direct current type. And direct current type should depend also on the earth field, for instance. So it should be subtracted from the sensor output. The main advantage of these systems is that there are no blocking. There's no blocking with it. There's no line of sight restriction like with optical systems. You get continuous data. Furthermore, the sensors are small and light. They don't weight very much, and they have a high update rate, about 200 Hz. Also a low latency, about 3.5 milliseconds. The price depends on tracking range, but these devices can be relatively inexpensive. And they are off the shelf available. So the wireless form is also, of course, more expensive. The main disadvantages are the problems caused by the high strength magnetic fields they are used. So you can have distortions. They can occur due to a lot of ferromagnetic material in environments, which will alter the fields and consequently result in not accurate distance and orientations. This device also tends to give less accurate readings the further the sensors away from the transmitter. Then you get yet on the boundaries. Here you see a visualization of the distortion of electromagnetic fields. It can be very big. You see, it can be 15 centimeters. Here you see some products of magnetic tracking. The oldest company is Essential. In our cave we use this tracker, and we also have a smaller one for the practical work. You can use it, try it out. They have also a wireless system, and it's possible to get about 20 sensors in one mechanical tracking system. So you can do some motion capturing. I think the price is about 65,000 euros to buy that. So another company and competitor of Essential is Polemis. They have 3 types, or maybe more: fast track and side track, long ranger. And, here's a website, so let's look at this. So you see they use medical simulators. So also tracking devices with police training, etc. So here you can find the Essential website. Some information you can read. Yeah, magnetic tracking was also implemented in the Razor Hydra. You know that device. It's very popular with the Oculus Rift. So it's also a magnetic tracker. Acoustic tracking. Acoustic tracker is a non-contact position measurement device that uses an ultrasonic signal. So that's produced by a stationary transmitter to determine the real-time position of the sensor. So it gives a brief ultrasonic pulse. So you need a sound transmitter and several microphones to record that sound. And it's a cheaper alternative to magnetic trackers, but it has some drawbacks. For example, it requires a line of sight, and hand tracking is then a problem due to frequent collisions that can happen. It is also error prone of noise and reflection of other sources, because they can falsely be identified as signals. Think about monitors or drives. Of course, speed of sound in air depends on temperature and air pressure. The equipment has to be calibrated before use, else have a built-in mechanism to sense or account for temperature and pressure. You can see it in the formula here on the slide. However, the biggest drawback with acoustic tracking is the slow speed of sound pulse, because at 0 degrees Celsius the speed of sound is 331 meters a second, and this in a typical working volume it could take 10 until 20 milliseconds for a single pulse to be sent and received. That may not be fast enough to track rapid movements accurately. So it has some drawbacks, this system. Mechanical tracking. So tracking may also be accomplished through mechanical means. For example, like you see here in the sheet, an arm-like boom may be used to measure the head position, and the user can strap part of the device to the head, or they can just put their face up to it and grasp the handles, like you see here. Mechanical tracking systems measure the position and orientation of an object that's attached to the end of the moving mechanical arm, and the arm is joined at a fixed position of reference, and it's made up of several sections that can rotate and move at the joints. The rotation and movements are measured and used to compute the position and orientation of the object relative to a fixed point of reference. And because of the strong binding between the user and the system is quite fast, about 5 milliseconds accurate, with an update rate of 300 Hz. It has barely jitter or latency. And also an advantage is that it's quite simple and easy to use and not expensive. But the major disadvantages of a system, of this type of system, is the physical linkage restricts the user to a fixed location in the world. For high fidelity VR, I think that the optical system offers the best attributes. Optical systems rely on measurement of reflected or emitted light, and these systems have, like acoustic systems, two components, light sources and optical sensors. And the light sources might be passive objects that reflect ambient light, or active devices that emit internally generated light. So multiple cameras can be used to track the position of an observer or an tracked object. And modern optical systems are real-time, use high resolution, high frame rates. The cameras sample the tracked volume to get a high spatial and temporal accuracy. It's about less than 1 millimeter and 10 milliseconds respectively. So these optical techniques are very reliable and used in medical domain. There's very latency, but you need enough cameras due to the blocking problem. That's the same as with the acoustic system. Also, the configuration of an optical tracking system can be very hard because of all the parameters. Think about the amount of cameras, the position, the direction, background noise, and all kinds of markers. You see the Oculus Rift. It has a camera and markers on the front side, and movement is limited using the Rift because as soon as not enough LEDs are inside of the camera, the software has to rely on the data of the Rift sensors. But the Rift only is able to track your position as long as you're facing its camera. And here you see the HTC Vive. The main difference between the Oculus Rift and this one is that the infrared lasers transect the whole space with 60 Hz. The Vive headset and controls are covered with detection points that are just photosensors, and they detect the flashes of that laser beams, so they know exactly where you are within that space. So this technique is also used with our motion tracking system. We have 12 cameras that have 26 pulsing LEDs at 100 Hz with a field of view of 46 degrees. The markers on the user reflect the light, and the distance can be calculated. And here you see the visual system. We have that too, and they have active LEDs that are recognized by 4 very high precision cameras. Okay, the last subject of this week, that's motion capture. Motion capture is the acquisition of movement. It's a technique of digitally recording the movements of real things, usually humans. And it is the 3D recording and 3D representation also of kind of live performance. And mocap is a visible tool for creating animation. And it's increasingly important as a source of motion data for computer animations, games, movies, and real-time TV broadcast. Note it can be based on any tracking method, but mostly cameras are used with reflectors or active LEDs. There are many ways to digitize motion. Most of them combine the use of hardware and software to capture movement, and we use the OptiTrack system, that's an optical system, to capture the motion. So an optical system uses an arrangement of cameras to track the information. Most optical systems track reflective markers. The system then combines the information of these views of the tracked marker to describe the 3D position of the objects. And by repeating this several times a second, the system can provide a volumetric trajectory of the marker according to time and space. and most optical systems can capture anywhere between 30 and 120 frames a second. The minimal amount of cameras needed to track an object is 2, but note that if a non-transparent object is carrying markers, a 2-camera setup is unable to see the ones that are pointing away from the cameras. A marker that does not be seen by a camera is called a cluttered marker. And then use a 4-camera setup that will fix the problem. The physical space where the cameras can combine their fields of view in order to describe the position of a marker is called the capture volume, as you can see here on the slides. As a general rule of thumb, the camera system has, as it has more cameras, the chance that more and more cameras can track the markers. So the bigger the volume can be. 8 to 16 cameras provide a good basic volume, but 16 to 32 cameras work better for video game scenarios, and for motion pictures over 200 cameras are used. One of the strengths of an optical system is the possibility to capture everything you can put markers in. So you can capture, of course, humans, but also dogs or horses, call something. When dealing with humans, you can think of every optical part of the performer as a separate object. 3 or more markers are to be applied for articulated section whenever possible. For example, on a hand. Note that the marker can make a part of more than one section, so you can put 3 here and there, but the 3rd marker can also be for the underarm. The arrangement of markers on a performer's body is called a marker set, and it's important to note that there's no universal marker set that works for every possible motion capture situation. So the marker set here works well for walking, talking, and maybe running or some acrobatic movement, but the markers get occluded when the performer crouches, arcs their back or lays on the ground. So that's it for today, for this week. See you next time.